Welcome to another learning session. Today, we are going to learn about containers. Almost all of you would have heard about at least Docker. Docker is a container technology. We will see what container technology is in today's session. When we need additional management or coordination capabilities such as availability, failover, and all those things, you will need somebody to orchestrate all these things. That is when tools such as Kubernetes comes into picture. Kubernetes is definitely a market leader, and knowing Kubernetes can get you very good opportunities within your same company or even in a different company. If you just search for Kubernetes opportunities, there are a lot. Before jumping into Kubernetes, let us understand what containers are all about. Once you have a clear understanding of what containers are, then you will be able to properly understand what container orchestration is. As I mentioned, almost all of you know what Docker is, at least have heard about Docker is. How many of you have heard about Podman? Also, how many of you have heard about Containerd? And how many of you have heard about runc? These are all either a container engine or a container runtime. So we'll be looking into all these things in today's session, because Kubernetes is not just a tool for orchestrating Docker containers. It can orchestrate multiple container technologies, and Docker is just one of them. First, we will look into what containers are, and then towards the end, we will look into what container orchestration is. Containers 101. 101 sessions are a naming pattern that is used for sessions that are the beginning sessions or the fundamentals sessions, which means you don't need any background of that particular topic. For example, when you say containers 101, this is the first session for containers. We'll be discussing the fundamentals, and you don't need any background or knowledge of containers. So today's agenda: a quick look back into traditional IT infra. We'll also look into server virtualization and hypervisors. We'll see how virtual machines are different from containers. We'll look into some of the container core concepts. Then we will look into some of the popular container solutions, like the ones we talked about, right? Docker, Podman, Containerd, runc, etc. And then we will look into a standard called as Open Container Initiative. Finally, we will also look into the need for container orchestration. If you are new to my sessions, I am Hartin Ganigatotu. I've written few books. I've got some certifications, and you can learn all about me from hartin.github.io. Working with traditional IT infra or on-premises. You can consider on-premises as your home. So forget about data centers and all. Consider that you need to set up a IT backend infrastructure at your home, and you need a server. What would you do? You will buy a server. And then the server will need an operating system. What will you do? You will install operating system, and you will have to patch them regularly. What do you mean by patching? For every operating system, their respective owners will release a patch if they find any bugs or security issues within that operating system. You need to patch it regularly to prevent other people from misusing that vulnerability and then logging into your system and then doing something you don't want them to do. So third, if you need to run any application, then you need to install that application along with all of its dependencies, and also configure these dependencies everywhere you need the app. So which means if you have 3 servers, you'll have to configure it 3 times. And if you have 4 servers, you'll have to configure it 4 times. If you need scalability, what do you mean by scalability? Scalability means if you have more load, you need to handle that extra load. So there are 2 kinds of scalability. One is horizontal scaling and one is vertical scaling. Vertical scaling means you add more resources. For example, if you have a computer and it is running on 8 GB RAM, so you are upgrading it to 16 GB or 32 GB. And if you have a machine, and to handle more loads, if you are adding more machines of the same capacity, then you are doing a horizontal scaling. We have discussed scalability and all as part of Cloud Computing 101 session. And we will be discussing it much more deeper as part of our Azure and AWS classes. Whenever we discuss about the components within Azure, AWS, and other clouds that can help in implementing scalability. And with the horizontal scaling, when you have more machines, what you'll have to do, you'll have to put something called as a load balancer and then balance the load. Whenever you are adding these extra machines, those extra machines also needs to have all these apps, dependencies, and all these things ready. When you have more apps on the server, resource utilization issues can happen where few apps use more resources. Then again, you will analyze which apps are creating those issues, and then you may be moving some of these apps to a different server. And again, in those new server, you'll have to do all these things. For that new server, you'll have to buy that server first. You'll have to install OS, patch them regularly, and install the app and dependencies and all these things. With cloud, some of these things have become easier for us. You have various different levels of abstractions that we have learned in Cloud Computing 101. Infrastructure as a service is the first level of abstraction. You don't need to worry about buying a server or anything physical. You will be getting a virtual machine. You'll have to manage that virtual machine. Patching the operating system and all those things you still have to do, but you don't have to worry about hardware. Virtual machines came as part of a technology called as server virtualization. With server virtualization, one host machine, imagine that your laptop, can now contain multiple virtual machines. So here with the server virtualization, one single machine can have multiple virtual machines, and all of these virtual machines can have different operating systems. One virtual machine may be running on Windows, one machine may be running on Linux, and so on. And this allows sharing of resources of a single host machine efficiently with the multiple virtual servers and has made cloud computing possible. So if your cloud computing provider had to provide one computer, one physical computer per user, it would not have been possible for you to make any kind of cost benefit, right? So why do we use cloud? It is mostly to save cost in one way or the other. Most importantly, you will be saving money on the time for which you are not using the cloud services. For example, if you are creating a virtual machine now and you are stopping that virtual machine after 1 hour, then you don't have to pay for remaining of the hours. But in your on-premises workload, if you buy a server, after 1 hour, you cannot give back. Go and give back to those shops and say that, okay, my use is over, you take it back. Okay, some shops may take it back, but at a much lower rate. All these sharing of resources made cost optimization possible and made cloud computing something that is desirable for everybody. VMs are managed by software components called as hypervisors. So there are two kinds of hypervisors. Type 1 or bare metal hypervisor allows running different VMs on top of a bare metal host machine. What do you mean by a bare metal host machine? Bare metal host machine means your computer without any operating system or other software. On your computer, you will have this hypervisor or a type 1 hypervisor managing some number of virtual machines directly. These virtual machines will have their own operating systems inside them. Type 2 hypervisor allows running different virtual machines on top of another operating system. So here, your bare metal is there. On top of it, some operating system is there. On top of it, you will have another VM running, and this VM is run using this hypervisor called as type 2 hypervisors. So if you have only a Mac machine and then you need to run some software on a Linux machine, then what will you do? You will need to run a VM on top of your Mac machine that is having Linux operating system. We'll see some of these things when we learn about Kubernetes and setting up Kubernetes on a local machine. Examples for hypervisors. Examples for type 1 hypervisors. VMware hypervisors like vSphere, ESXi, ESX, Microsoft Hyper-V, Oracle VM Server, Citrix hypervisor, etc. And examples for type 2 hypervisors include VMware Orchestration, VMware Fusion, Oracle VirtualBox, Oracle Solaris Zones, etc. So we'll be seeing two of them here, VMware Fusion as well as Oracle VirtualBox when we see the setup for Kubernetes in local machines. In summary, you have type 1, which means you have to first have it before installing your virtual machines. Type 2 is mostly for testing, learning, development, and all those purposes, where you already have a machine with the operating system, and then you need another virtual machine for some other purpose. So some of the problems with virtual machines that led to containers, first of all, the need for lightweight VMs. Starting and stopping regular VMs may not be appropriate in all cases where performance is critical, such as serverless computing. Hence, there was a need for lightweight alternatives to regular VMs. We looked into few different abstractions in cloud before, right? At least from a high-level perspective. In infrastructure as a service, which is the first level of abstraction, all of your physical things are abstracted away from you. So you don't have to worry about anything physical, like buying hardware or maintaining hardware or anything. You have to only worry about managing your virtual machines. You'll have to do all the things that you need to manage within that virtual machine, including patching the operating system and all. And the next level of abstraction was platform as a service. If you move to platform as a service from infrastructure as a service, you don't have to take care of patching your operating system and all. You just take care of your applications. You can say that I need to work with Java applications on a Tomcat server, and then everything is just provided to you. So you have to worry only about developing that Java application and deploying it to this platform as a service offering. Or you can say that I need a .NET application, or I need to work with a Python application, etc. And if the platform supports it, then it will allow you to do the deployment. For example, if you consider a cloud computing platform like Azure, Azure has a platform as a service offering called as Azure App Services that does all of these things. When you say deploying an application, you'll have to create that application. So if you are a Java developer, then you'll have to create an application using some framework. Spring is definitely the most popular today. So if you look into the code of that Spring-based application, you will see that there will be a lot of code. Some of these have been written by the Spring team, and then they have given it to you as a bundled jar. And still, you'll have to write a lot more of code for managing these things. So for example, if you need to create a RESTful API, RESTful API is a way of communicating with the server. You will see REST services later. You can make a HTTP request and then you will get the response back. Even for that, you will need to write a lot of code. The next level of abstraction is serverless. So in serverless, you don't need to worry about your physical server or even your virtual server or even your software server. You don't have to even worry about your application. So here, you don't have to build that application and deploy. You just have to write the code for whatever functions you need. And rest, everything will be taken care by your cloud provider. Serverless does not mean that there are no servers. There are still servers, but you don't have to manage it manually. So somebody else will be managing it for you. And in a public cloud, it is going to be that public cloud provider. That is not the only benefit of serverless computing. If you need to call something purely as serverless, you should be charged only for the time you are using the service. Imagine that you are having a website and you are selling certain things using that website. So unlike a physical store where you will close the shop at evening 8 or 9 or 10 or 11 and then go home, sleep, and then next morning come and then open the shop. Websites do not generally get shut down at night, right? They'll be running 24/7. So if you are using a virtual machine or if you are using a platform as a service to run your website, you will have to run these servers always. Sometimes we may have to build our applications. Meaning somebody will be writing code, and that code has to be compiled. It has to be moved through different phases, and finally it has to be deployed to a server. And these activities do not happen always, right? And that is where serverless computing can help. It says that, okay, if you are not using, don't pay. But then behind the scenes, your particular cloud provider, they cannot run a server or they cannot run something always and then ask you not to pay for it, right? So what does your cloud provider do? So they will need a lightweight VM technology that can start immediately, so that whenever you are using it, they will run it. And if you are not using it for say 1 hour, you can configure those with the most cloud providers. If you say that, okay, I'm not using this service for 1 hour, then shut down my lightweight VM or whatever technology that is running my service, and allocate those compute, basically your CPU time, to somebody else. Your CPU time will be allocated to somebody else, but your storage will still be charged. But in today's world, storage cost is very, very less. Your compute cost is the primary cost you will have in cloud. So you cannot have a regular VM for shutting down and then coming back. Instead, you will need something which is very light and very fast. And that is where containers come as a lightweight alternative to regular VMs. With serverless, there are few things that you need to consider, and then you need to see if that makes sense for your particular application. For example, first time when the request comes, whenever these lightweight VMs are started, or lightweight alternatives called containers are started, there will be little bit of a delay. The delay will not be same as your regular VMs, but still there will be a little bit of delay, and that delay is generally called as cold start time. Okay, so you have to analyze whether that cold start time is a problem for your application or is it okay. It depends from application to application. There could be many consistency issues during handoffs between different teams or environments such as dev, QA, etc. And that usually led to blame games referred to as not working in my environment. I used to be a developer. We used to develop things, test on my machine, and then ask QA to test it. When QA test it, they will tell, okay, it is not working properly. Then I will tell, or the developers will tell, okay, it is working on my machine. And then they will say, not, it is working on their machines. And sometimes when it is deployed to a production again, there could be issues where it may not be working the same way as it was working in our local machines or even test machines. It is because there are a lot of configurations, lot of dependencies. If one of the dependencies is missed in any of the environments, things will not work. If one of the configuration is missed in any of the environments, things will not work. That is where containers came. So containers came as a lightweight alternative to virtual machines. And virtual machines run a complete operating system, including its own kernel, as you know. Containers are built on top of the host operating system's kernel and contain only apps and some lightweight operating system APIs and services that are needed to contain the application and its dependencies in a portable way. In summary, this means that container will not have all the things that are there in your operating system. It will only have enough components to make it work independently with other containers. Each container will have a respective app and all of its dependencies and configurations, and it is portable, meaning you can take this container from here and you can install that container in some other machine, and all these apps and dependencies will be the same in this machine as well as that machine. So you cannot say that, okay, it is working in this machine and not working on that machine, because the app configuration, everything will be same everywhere this container is taken. So this container encapsulates everything into a single thing, and then that single thing is being taken away to different environments. When you compare differences, VMs are managed by hypervisors, as we learned earlier, while containers are managed by a container engine. A container generally has a default application to start, which is not the case with the VMs. So when you start a VM, when you start your computer, you can decide what all applications to start by default or not start by default, and then you can start those applications on your own. But in general, containers will need some application to start when they are started. So when you start a container, some application needs to be there that will be started automatically, or the container will start and stop immediately. It is not like virtual machines where virtual machines will be started and then your desktop will be waiting for you to do certain things. So if you see this picture on the right, you see a lot of shipping containers, right? So imagine instead of using the shipping containers, putting all these things together into a particular ship, it will be complete chaos, right? Whenever they want to take things out. Categorizing and then putting things into different containers can help your shipping management company effectively transport things. So similarly, here your containers actually encapsulate your apps and dependencies. So it will take the same encapsulated thing to different environments and prevent consistency issues and the problems such as not working in my environment. Containers help in efficient implementation of architectural patterns such as microservices. So with cloud computing and container as a service, scaling can be configured automatically without worrying about the steps needed with the traditional IT infra and performance issues with a VM. In cloud also, you will have services that will help you manage containers and that will take care of your scaling problem. So you can say that, okay, if one container is not able to handle my load, automatically increase the number of containers. You can configure all these things in most of the cloud providers. So when you combine cloud computing with containers, you are going to get a lot of benefits. We will learn about microservices in a different session. In summary, a big application is split into small applications. And each of these small applications take care of one functionality. And each of these small applications can be managed by different teams. And each of these small applications can run on different technologies. So before this thing called microservices came, there used to be something called as monolith applications, which means there was a very big application that took care of all the business related things for a particular company. But what was the problem with that? So imagine a website such as Amazon or Walmart or Flipkart, where you can buy things. Do you think the number of people who are surfing that website or checking the products will be same as the number of people who will be actually buying products at any particular point of time? No, right? Number of people checking the website will be huge, and only a very small portion of the people will be actually buying product at any particular point of time. So there are two functionalities that need two different kinds of scaling. So for the part where you are viewing your application, you need a lot of scaling. And for the part where you need buying, you need less scaling. And also, it could be okay for you to have some discrepancy in the numbers during that exploring phase. But whenever you are buying certain things, your provider has to make sure that you are only selling things that they have in their stock. For example, you may be seeing that, okay, there are 2 items for this product. And when you go to your checkout page, you see that, okay, it is already bought by somebody else. That is still fine. But if you are buying a thing, paying money, and then your provider is telling, okay, sorry, I mistakenly sold the one item I had to 2 people, so one of you will not get it, that is bad. So the consistency also can be different between these two functions. When the consistency requirements change, you'll have different kinds of technologies to build these two functions. So that is not possible with the older monolith. So now if you have two different services or two different applications, you can have different sets of technologies, and you can easily connect them using some connectors like HTTP or a messaging queue, etc. So all these things we will discuss when we learn about microservices. And also you have very big application, one application for the whole big company, and every team making a change can affect other teams or other products or other services that the company has. That is also an issue, right? If you have smaller applications, then whatever issues that the application face will be limited to that application only. It will not affect other applications. So that is also another issue that microservices solve from the traditional monolithic applications. But microservices is not the solution for every problem, and every product doesn't have to be starting as a microservice. You can definitely start as a monolith, and then you can move to microservices. Let us get started with container core concepts. So first one is container image. We talked about encapsulating apps and dependencies into a single package and all those things, right? So that is done through images. So images are packages or templates that encapsulate all that is needed to run that application. Example, the application itself, its dependencies, its runtime environment, etc. These images are immutable, which means they are read-only. Each modification adds a new layer to the pre-existing layers. But initially, you will be mostly using images that are created by somebody else. Containers are the actual runtime environment instance based on the images. So the images, you can just consider them as a template. And earlier, I told you, right, you'll be using containers created by somebody else. So how will you get that? There are many registries. Okay, container registries are used to store and share container images. Docker Hub is a popular public registry for Docker. So initially, when we learn about containers and when we learn about communities and all, you don't have to worry about creating these images. You will be downloading something from the registry, such as Docker Hub, and then you will be using it. Because with Kubernetes, our goal is not to create containers, but to manage them or orchestrate them, right? But if you are interested in knowing more about how actually that container is created or container images are created, then we can definitely have sessions on that also. And most cloud providers also offer private container registries. For example, Google has Google Container Registry, AWS has Amazon Elastic Container Registry, Microsoft has Azure Container Registry. And these registries are private within that particular cloud. And you can allow people whom you want to use that container registries to create containers from those images. The operating system is abstracted away by a container engine. So with Docker, you are not directly communicating with your operating system, but you are communicating directly with your Docker engine. A container talks to the container engine and not the operating system directly. So that way, your container is abstracted away from operating system. There are two terms here, right? Container engines and container runtimes. The high-level container engines such as Docker are used by the end users to manage the images and containers. These high-level container engines usually make use of low-level container runtime to actually communicate with the operating system. So a lower level container runtime is generally used within a container engine for actual container lifecycle management activities, such as creating and running containers. The container runtimes abstract the Linux primitives and are not designed to perform additional tasks than starting the containerized process. Once the containerized process runs, the container runtime is not required to perform additional tasks. Even though a container runtime can be used within a container engine, so Docker will be having a container runtime inside it. These container runtimes can also be used by hand without a container for testing and similar purposes. So the most popular low-level container runtimes include runc, cron, containerd, etc. Docker, CRI-O, and many other container engines currently rely on runc. Container engine is somebody who is managing things from an outside perspective, and we talk directly to that outside manager. Assume that you have gone to a restaurant and you are telling the restaurant waiter, I need a orange juice or something. That waiter will go inside and tell somebody else to actually prepare it. So here, that waiter who is coordinating things can be considered as a container engine, and the actual person who is actually preparing can be considered as a container runtime. And sometimes you may be directly telling the person who is preparing to prepare it for you. Okay, that is also possible. Similarly, in our world, so sometimes you may be directly using one of the low-level runtimes for some of your testing rather than testing it through the high-level container engine. More on containers and Linux. Containers are generally built on top of Linux kernel features and can be considered Linux themselves. Containers use Linux features such as namespaces to provide isolation, CG groups to provide dedicated resource allocation, etc. Even if you are running different containers on the same operating system, all of those containers should be isolated from other containers, right? For that, they use native Linux features such as namespaces rather than reinvent the wheel and create a technology of their own. A container's host platform is typically Linux. In Windows or Mac, Linux is offered at host level through virtualization. Containers can also use minimal Linux distributions such as CoreOS and Fedora Atomic. Many public cloud providers and many container orchestration solutions such as OpenShift uses these minimal OSs. One question. Docker is one of the most popular container engine and even made containerization popular. So can you name some of the other container engines or other container runtimes that are available? During the session itself, I have mentioned a few other names. Let us see some of the popular ones. So some of the popular container solutions include LXC, Systemd-nspawn, Docker, Podman, CRI-O, runc, containerd, Windows Server containers, Hyper-V containers, CoreOS RKT, and OpenVC. Some of these are high-level container engines. Some of these are low-level container runtimes that can also be used by hand for testing. Docker in a slide. Docker uses a daemon. What is a daemon? It is an ongoing program running in background to create images and run containers, etc. So somebody is running always in the background. Docker uses a client-server architecture. The Docker client is responsible for communicating with the Docker server. Docker has community and enterprise editions. So these days, most of the software will have community and enterprise editions, right? One will be free, one will be payable. So that is how those companies can run, right? Without money, nobody can run any business. Docker file is a file with all instructions to build an image. Instead of distributing images, we can distribute this Docker file. You have a lot of steps to create an image and all those things you can mention in Docker file. So rather than giving the complete image, you can just give this Docker file, and then this Docker file will pull those things and then build that image. Also, Docker images can be stored in a repository such as Docker Hub. Podman follows a daemonless architecture. In Docker, we saw, right? Docker always needs a daemon or background process to run. Podman follows a daemonless architecture to run containers under the user starting the container. Podman allows users to create pods. A pod is a way to group containers together under a common organizational name. So we'll learn this concept of pod for organization containers when we learn about Kubernetes also. With Podman Docker, it is a tool. You can run Docker commands with Podman. Basically, it will create an alias. So if you have learned only Docker and if your platform do not support Docker, the latest versions of Red Hat 8 and CentOS 8 and all do not support Docker. If you have learned only those commands, you can use Podman Docker for time being to use those same commands to work with Podman. So Docker versus Podman. Docker uses a daemon, an ongoing program running in the background to create images and run containers. Podman has a daemonless architecture and can run containers under the user starting the container. Docker has a client-server logic mediated by a daemon. Podman does not need that mediator. As Podman has a daemonless architecture, it doesn't need a root access and runs in a rootless mode by default, but can run root containers also. In Docker, daemons have root privileges, making them a preferred getaway for attackers. However, Docker recently added rootless mode also to its daemon configurations. So we learned a few other terms also, right? A quick peek into each of those. LXC, Linux native containers with initial release in 2008. Systemd-nspawn, used to run a command or OS in a lightweight namespace container like chroot, but it is more powerful. runc, created by Docker and the OCI, is a low-level container runtime. Containerd, as of February 28, 2019, Containerd is a graduated project with the Cloud Native Computer Foundation. So what is this Cloud Native Computing Foundation? It is a foundation that also manages Kubernetes now. It is a low-level container runtime, Containerd. CRI-O is an open source implementation of a Kubernetes runtime interface CRI. It allows you to run pods using OCI compatible runtimes. Windows containers and Hyper-V containers, lightweight alternatives to Windows virtual machines, available on Windows Server. RKT, application container runtime engine, that features a pod native approach. RKT's pods are synonymous with the concept in the Kubernetes orchestration system. OpenVC, container-based virtualization for Linux. So unlike VMware, Xen, and KVM that provide full virtualization, OpenVC uses a single Linux kernel and provides minimal virtualization. These are some of the popular container solutions. So there is a question, can you explain about root? So root means a user in a Linux environment that has permission to do everything. So there will be a root user with permissions to do everything in that particular operating system. And there will be other users, they will only have certain permissions. So for example, certain users may not need to delete files in a particular directory. So in Linux, you'll have different permissions. In summary, you have an operating system, and then you have the root user with all permissions. And then you create users for maybe all of the people attending this session. And all of these people attending the session who are getting a user in that Linux machine may not need all the permissions, right? They'll be given permissions as per the need. Docker, it needed that root permission to run that daemon, and then basically that means this daemon has all the permissions, right? So all the permissions is always something that people doesn't want to give. Assignment number 1 for all of you. Prepare at least one slide on each of the below container solutions and take a session to the CloudRig study group if you are part of. And when you do that presentation, the trainers or your mentors can also understand your presentation skills, and then they can help you improve. You will be learning a lot of things about containers when you actually search for these things in Google. And sometimes you may also get new questions, new doubts that also you can share in the group. So Open Container Initiative, OCI. Open Container Initiative is a Linux Foundation project started in 2015 by Docker to design open standards for operating system level virtualization. Most importantly, Linux containers. OCI allows containers from one engine to run in another engine. So containers built for one engine can now run in another engine also. The low-level container runtime component is generally implemented according to OCI specs. So that is why you can switch between different container runtimes. The OCI runtime standard reference implementation is runc. We saw, right, many different container engines were using runc. So do you remember which all container engines were using runc? Docker was one of them. A quick peek into history. When Docker engine was first created, it relied on LXC as the container runtime. LXC also we saw in that list, right? Later, Docker team developed libcontainer to start containers. Finally, when the OCI was created, Docker donated the libcontainer code and turned it into a standalone utility called as runc. Need for container orchestration. For an application to work in a production, you need many features, right? You need high availability, you need scalability, you need storage orchestration, you need automated rollouts and rollbacks, you need service discovery and load balancing, you need a self-healing, you need batch execution. And to do all of these things, if you are going to create a software or if you are going to do it manually, it will be very, very difficult. So it is good to have someone manage and orchestrate containers, and that is where container orchestration comes. So examples of container orchestration platforms include Kubernetes is one of the most popular container orchestration tools. Docker Swarm is another container orchestration tech that is specific to Docker. And there are also many managed container orchestration platforms such as AKS in Azure, GK in Google, EKS in Amazon, and also Red Hat OpenShift. Assignment number 2, which is optional. Find more container registries, public and private, than discussed here. Also find minimal Linux distributions used by public cloud providers, AWS, Azure, GCP, and by Red Hat OpenShift. Third one, find more managed container orchestration solutions than discussed in this session. So today, we had a quick introduction to containers and some of the container technologies. And as an assignment, you will be exploring about these containers and present in our study group. And members of the group can join, they can give feedback, they can learn from you. So that is how we learn and grow together. Let us learn together and grow together. See you all in the next session.